Hello, this will be a demonstration of Proposition 11 from Book 7 of Euclid's Elements, which says that if a whole number is to a whole number as a part subtracted is to a part subtracted, then the remaining number shall be to the remaining number just as the whole is to the whole. We have two numbers, AB and CD, and from them we shall subtract proportional parts so that the number AB is to the number CD, just as the number AE is to the number CF. And what we're going to prove is that the remainder is to the remainder, just as the whole is to the whole. Now, if we subtract the number AE from the number AB, our remainder will be the number EB. And if we subtract the number CF from the number CD, we shall get the remainder FD. So that what we're going to prove is that the number EB is to the number FD, just as the whole number AB is to the whole number CD. Now, the text of Euclid assumes that the number AB is less than the number CD, and so it has to be part or parts, but this proposition works equally well if AB happens to be a multiple of CD. But we're just going to work with the case where AB is less than CD. So, the number AB being to the number CD, just as the number AE is to the number CF, this was given to us. It then follows, by virtue of the definition of proportionality for numbers, that the first is the same part or parts of the second, that the third is of the fourth, so that the number AB is the same part or parts of the number CD, that the number AE is of the number CF. And this being the case, if either of these is the case, let's say that if the number AB is the same part of the number CD, that the number AE is of the number CF, we can then use proposition 7.7 to say that the remainder is the same part of the remainder, that the whole is of the whole, so that the number EB will be the same part of the number FD, that the number AB is of the number CD. And likewise, if the number AB happens to be parts of the number CD, then we can use proposition 7.8 that the remainder will be the same parts of the remainder, that the whole is of the whole, so that in total, the number EB will either be the same part or parts of the number FD, that the number AB is of the number CD. And this being the case, it then follows by definition 720 that because we have a first being the same part or parts of the second, that a third is of a fourth, we can then say that the first is to the second, just as the third is to the fourth, again by definition 720. So we can say that the number EB is to the number FD, just as the number AB is to the number CD. And this is precisely what we set out to prove, which means we're done with the proposition, therefore, etc., QED. Now, an example of this would be if we had 18 is to 28, just as 6 is to 8. And then follows that 18 minus 6 is to 24 minus 8, just as 18 is to 24. Now, 18 minus 6 is 12. 24 minus 8 is 16. So that 12 is to 16, just as 18 is to 24. And this is true. So we see that the proposition holds. A few other things to say about this proposition. If we wanted to cover the case where the number AB is greater than the number CD, it's either a multiple or it's what would be called an improper fractionale. So an example would be 8 to 6. There's not a name for this. The most logical one, I suppose, would be that 8 is multiples of 6, but that sounds strange. But it works in just the same case. What we would do for that is we would just invert the proportion. Unlike Book 5 with magnitudes, there are a decent amount of properties about numbers and about proportions of numbers that don't need to be proven. So, for example, we're not going to find the equivalent of 5.7, 5.9, or 5.11 within Book 7. But we will find some propositions that are analogous to Book 5 propositions, such as this one, which is exactly the same as as proposition 5.19, except magnitude is swapped out for number, because we're in the book on number theory, not magnitudes. Why Euclid does this is the simple fact that numbers aren't magnitudes. This is quite obvious from the fact that number is not continuous. If you have like some number 3, you can't divide it up at just any point and still have a number. Whereas with like a line, for example, which is an example of a magnitude, you can cut it at any point and it'll still be a line, but this is not the case for numbers, so numbers are not magnitudes, which means that we can't just assume properties of magnitudes and say that they apply to numbers equally. Excuse me. Okay, I had one more thing to say about this proposition, but I've forgotten it. So I guess I've got nothing more to say about this proposition, so I'll end the video here and move on to 7.12.